Hello everybody, my name is Justin. I'm here in beautiful Horner, West Virginia and McFly's Outdoors in Lewis County, West Virginia. I'm going to be taking some calculations for my final project for this physics class, and I'm going to be calculating the spring potential energy of a compound bow and then the kinetic energy, translational kinetic energy of an arrow. So we're going to have this spring potential energy go from the bow and transfer to kinetic energy of the arrow. These compound bows have cables. As you can see, this is the string, this is the cable. Spring potential energy is stored with the tension of this string and the cams or the wheels and the actual tension of the limbs. So without further ado, we'll go ahead and we are going to measure the draw weight of this bow. We're going to measure the draw length of this bow with measuring this arrow, and we're going to weigh these arrows. We're going to get the mass of these arrows, and then finally we are going to go ahead and shoot this bow. We're going to put an arrow in it, we're going to shoot it, and we're going to use a chronograph machine to measure the actual speed of the arrow out of this bow. Everybody, before I take these measurements, I just wanted to go into a little bit more detail on the materials that we'll be using for this experiment. This is a aluminum and carbon arrow with a 100 grain field tip. There's actually aluminum on the outside of the tubing of this arrow with carbon on the inside. This is a compound bow that is estimated to have a draw weight of 70 pounds. This is the string, these are the cables, these are the limbs, and the cams on both sides. So you would have spring potential energy stored with the tension or the compression of these limbs, and then the tension of the bowstring. This arrow, once it is shot, would have translational kinetic energy. Just wanted to give you a little rundown on the materials that will be used for this experiment. As you can see, we are measuring the weight of this arrow, which will later be calculated into mass. And we have a digital scale here. And the total weight of this arrow is 33.165 grams. All right, everybody, we are now measuring the distance that the string will travel with a nocked arrow. So we're going to go ahead and have the bow technician draw the bow back using a hooter shooter. This instrument is used to tune bows, and it takes the human factor out of tuning a bow. And I believe it's drawn back all the way. So if you would, sir, if you could hold this camera, I'll go ahead and measure. Let's see here. So there's where the arrow is on the rest. And I have exactly, if you could get the camera angle on the nocking point, 61 centimeters. Go ahead and stop. Ready? Okay. Now we're going to be measuring the draw weight of the bow, the true draw weight. It's measured in pounds. Okay. Did it take the calculation?
Yeah.
Okay. And 70.6 pounds. The next thing we're going to do is we're going to measure the speed of the arrow using a chronograph. This is going to be in feet per second. So here we go. So if you would move up here. 247 feet per second. All right, everybody. That concludes the measurements. I want to thank McFly Outdoors over in Horner, West Virginia, for letting me use their archery shop. And in summary, we calculated the draw weight of this bow, the weight of this arrow, the draw length of the string, and then also the speed of the arrow to get our measurements. Now the next step will be doing the conversions and the calculations to find the spring potential energy of this compound bow and the translational kinetic energy of this arrow. Thank you. For my final project, we are calculating the potential spring energy of a compound bow and the translational kinetic energy of an arrow that is shot from the compound bow. Here are the formulas that will be used. Spring potential energy equals constant divided by 2 times change in distance squared. Here's Hooke's law to find the spring constant. And then translational kinetic energy, mass divided by 2 times speed squared. Here are my measurements and conversions, the conversions of the measurements that you saw earlier in the video. The distance traveled by the string, we'd measured it as 61 centimeters. We convert that to 0.61 meters. The draw weight of the bow, which was according to the scale, 70.6 pounds. We divide that by 2.2, which gives us 32.024 kilograms. We multiply that times 9.8, which gives us a draw force of 313.84 newtons. We chronographed the speed of the arrow, 247 feet per second. We divide that by 3.281, which gives us 75.286 meters per second. And then here we have the mass of the arrow, which on the scale was 33.165 grams. We multiply that or convert that into kilograms, which gives us 0.033165 kilograms. Here is the problem statement. What is the spring potential energy of a compound bow that has a draw force of 313.84 newtons and a string that travels 0.61 meters during each shot cycle from full draw to rest after release? Use Hooke's law to determine the spring constant. What is the translational kinetic energy of an arrow that has a mass of 0.03165 kilograms and a flight speed of 75.286 meters per second? Here is the solution. We apply, to find the spring constant, we apply Hooke's law to determine the spring constant for spring potential energy. Here are the knowns. The force of the bow is 313.84 newtons. The distance of the string, that it travels is 0.61 meters. We don't know what the spring constant is. We're trying to find that. And the SI unit is Newton meters. Here's the formula for the spring constant. And then we go ahead and convert that to find the spring constant. And here we go ahead and plug in the numbers. 313.84 newtons divided by 0.61 meters, which gives us 514.492 Newton meters. So that is the spring constant. Here is, as we continue on for the solution for part A, we apply the spring constant, or the spring potential energy. Here is the formula for that. We plug in the known spring constant. And once again, here is the formula. Here are our knowns. The distance of the string is 0.61 meters. The spring constant is 5.14.492 newtons meters. And then the SI unit is Newton meters. Go ahead and plug in the knowns. 0.5 times 5.14.492 Newton meters times 0.61 meters squared, which gives us 95.72 newtons meters. And that is the spring potential energy of the bow. Solution for B is we're going to apply translational kinetic energy, which is going to be 1/2 of the mass times speed squared to find the translational kinetic energy of the arrow. Here are the knowns. The mass of the arrow is 0.033165 kilograms. The speed of the arrow is 75.286 meters per second. The SI unit is joules. Here's the formula once again. Go ahead and plug in the numbers. 0.5 times 0.033165 kilograms times 75.286 meters per second squared, which gives us a translational kinetic energy of the arrow, which is 93.989 joules. And then the discussion for this problem. Here we see that a compound bow with a draw force of 313.84 newtons, and that has a string that travels 0.61 meters during each shot cycle from full draw, transfers 95.72 newton meters of spring potential energy from the string to a 0.033165 kilogram arrow. The spring potential energy is then converted to translational kinetic energy onto the arrow as it moves off the string and flies at a rate of 75.286 meters per second, which yields 93.989 joules of translational kinetic energy. So once again, the spring potential energy of the compound bow is 95.72 newtons meters. And the translational kinetic energy of the arrow is 93.989 joules. Thank you. All right, everybody. This concludes my experiment of the spring potential energy of a bow and the translational kinetic energy of an arrow. Hopefully, this clarifies those two concepts.